Hi students, welcome to another video on control system. In this video we will see how do we model mechanical system. So we are considering a mechanical system being represented by mass, friction and a spring constant. Now so there is a force applied to mass m1 and this mass m1 is connected to mass m2 through a friction constant b12, and of course this m2 has a friction with b2 here with a rigid surface, and of course it also has a friction with the rigid surface which is b3, and of course there is a k2 spring constant which is connected to the rigid surface. Now we know that because of the applied force to m1, so there will be a translational displacement in the direction of the applied force. Let me just name it as x1, and this will have a displacement of x2. Naturally the x2 displacement will be lesser than x1 displacement, which is the usual phenomenon we're going to end up with. So let us name it as x1, x2 as the displacement of m1 and m2. Now before we start writing the Laplace transform of this particular system, so let us write a free body diagram which is indicating what are the acting and opposing forces on the mass on different masses. Since we have two masses, separate the masses which is available over here. So one of the mass is m1, the acting force on this is F, which is on the direction towards right side, and we will going to have an opposing force because of this translational motion. So due to this mass itself, so it is nothing but m1 into a1, which is nothing but the acceleration due to the displacement x1, and there is a friction with the rigid body, and that will have a opposing force due to this friction. So it is given by b1 into v1, that is the dash pot. Of course we also call friction as dash pot. This is friction, which is also we call it as dash pot. So that there is a dash pot indication. So of course it was seen, please indicate the friction by a cylinder and a piston so this is indicating there is a friction in this particular surface. So this is how a friction is represented. Spring, of course, using a coil type of structure, and of course this is mass. Now because this b1 has got a friction with the rigid surface, the effective displacement is x1 here. So we are going to have a velocity corresponding that x1 as v1, and you can see there is one more opposing force on this b1, which is due to this friction which is between m1 and m2. So since this dash pot is between m1 and m2, this will have a relative displacement which is x1 minus x2. So we will write it as b12 v1 minus v2. So v1 minus v2 is the relative velocity of this particular opposing force. Now we can replace. We know that acceleration is nothing but d square x by dt square, that is it is double derivative of the displacement. Similarly velocity is given by its dx by dt. So this is the derivative of the displacement, this is a double derivative of the displacement. So naturally this comes out to be m1. Of course we will also write this as x double dot, indicating that this this is a double derivative, and this we write it as x dot. Whenever we write double dot, this corresponds to double derivative. Whenever we write x dot, it's a single derivative. Since this is acceleration, let me write it as x1 double dot, so which is the double derivative. And of course here it is b1 into x1 dot, here it is b12 x1 dot minus x2 dot. So these are the three opposing forces for this mass m1, out of which this opposing force, which is due to b12, will act like the acting force on m2. So let us now write m2 mass. Now due to this applied force F, how it is passed on to m2 is, it is through b12. The one which was, the b12 was opposing the moment of m1, so this is the opposition force. So this opposing force will be the acting force for this m2. So the magnitude of the acting force of m2 is this one. Now what are the opposing forces for this m2? One is due to the mass itself, which I'll call it as m2a2, and this is due to this friction, it is b2 into v2, and this is again b3 into v2, and there is one more opposing force, which is k2 into x2. Since it is acceleration, velocity and displacement, you can write it as its derivatives. So it is now m2 x2 double dot, this is b2 x2 dot, this is b3 x2 dot, this is as it is. Now when we write the equation, we are simply writing the acting force is equal to the opposing force as per Newton law. So we write, you take the forces that are there for m1, which is nothing but F is nothing but applied force, is nothing but the opposing force, which is m1 d square x1 by dt square, which is double derivative, plus b1 into dx1 by dt plus b12 d by dt of x1 minus x2. This is my equation. You have to write its Laplace. So what is the Laplace of this? F of s is equal to, so we know that derivative, if it is double derivative, it is s square, if it is derivative, it is s. So it is m1 x1 of s square, and then it is b1 s x1 of s, and it is b12 s x1 of s minus x2 of s. So I can simplify this and write it as, and group it for x1 of s. Is it not m1 s square plus b1 plus b12, of course this is s is the coefficient, sorry, s coefficient are b1 plus b12, and it is x1 of s. And do you have this b12s x2 of s? This is the Laplace of this particular of course we know that this is called as free body diagram. This is free body diagram, indicating what are the acting and opposing forces on various masses. And again, if you want to write it for this, the acting force on that is, it is b12 d by dt of x1 minus x2 is equal to m2 d square x2 by dt square plus b2 into dx2 by dt plus b3 dx2 by dt plus k K2 into X2, K2 into X2. So this is my equation. So just have a look at it, take a pass, and then understand the acting force, which is this V12 d by dt of x1 minus x2. This is the opposing forces, which is this here, m2 into x double dot. X double dot is double derivative. It is b2 into x2 dot, which is a derivative of x2. Again b3 into x2 dot derivative, and k2 into x2, k2 into x2. Next you can take the Laplace. So it is b12 s x1 of s minus x2 of s is equal to, of course you can stop it here itself, no need to group. You can also group it and then put it as one more step. So let me just group it, because all of them have only x2, x2, x2. I can write m2 s square plus b2 plus b3 s plus k2 into x2 of s, x2 of s. So this is my final transformation for, this is one of the force equation, this is the other force equation, this is the other force equation, this is the other force equation. This is how you can able to make sure that you are writing a free body diagram very clearly. Don't simply write it as simply B1. It should be the force B1 into the whatever is the associated velocity with this B1. Since the B1 is the friction here, so you need to write it just underneath of mass with the rigid body, so that it indicates there is a friction. And then over here, and of course we have a friction over here. Similarly, of course, you can think of writing it for any circuit, any mechanical system. Similarly, we can think of writing it for a rotational system. So let us take a rotational system which is connected to a rigid body, something like this. So let us take, this is the rigid body what I'm having. Assume that there is a spring constant, and this is the representation of inertia of a particular system, and assume that this is a friction between the two inertias. So let us assume that this doesn't have any inertia, so this is connected with a free wheel, and let us write this as J1, this as B12, this as J2, this as K2, this as B2, and of course there is no friction here. So this is my torque that is applied in the clockwise direction. So because of this applied torque, I know that there will be an angular displacement in the same direction as that of the applied torque. Since it is going clockwise, this will also go clockwise, theta 1, and this will have an angular displacement theta 2. Next we need to write the free body diagram for this particular rotational system, for which you have the inertia J1 being applied with a torque T, and because of this inertia itself there is an opposing torque. Opposing torque is exactly in the opposite direction of this. So since it is clockwise, this will be in the anti-clockwise direction. So you can see the directions are exactly opposite. The opposing torque is J1 theta 1 double dot, theta 1 double dot. And similarly, there is no friction here since there is a free wheel connected, but there is a friction between J1 and J2 through B12, which will going to have, so now it's again in the same direction as that of the opposing force for this due to inertia. Now it is B12, the displacement is relative, but that means here it is theta 1, here it is theta 2, the effective displacement is theta 1 minus theta 2. So it is theta 1 dot minus theta 2 dot. This happens to be the acting torque for J2. So now you can see the direction of acting torque, it's clockwise, this is again the clockwise, and this is my J2 second torque, second inertia. What is the opposing force due to the inertia itself? It is J2 theta 2 double dot. How about due to this B2? So due to this B2, it is B2 into theta 2 dot, and due to K2, so it is due to K2 theta 2, K2 theta 2. Now it is, as we wrote it for the earlier case, we need to equate the acting torque and the opposing torque. Acting torque and the opposing torque. So acting torque is T here. Opposing torques are J1 theta 1 double dot plus B12 theta 1 dot minus theta 2 dot. So what is the acting force for the second one? It is B12 theta 1 dot minus theta 2 dot. So this theta 2 dot is derivative of the angular displacement. Of course here it is relative. So next it is J2 theta 2 double dot plus B2 theta 2 dot plus K2 theta 2. And its Laplace you can easily write. So for the first one you can write TFS as equal to J1 S square plus B12 of theta 1 of S minus B12 S theta 2 of S. This I have to write S here because Laplace of a derivative is S. So this is what you have. And for this one you have B12 S theta 1 of S minus theta 2 of S is equal to what? J2 S square plus B2S plus K2 multiplied by theta 2 of S. This is what we have. Right. So this is the acting torque, which is this. T. Opposing torques are this plus this, and of course its Laplace is given here, and this becomes the acting force for the second inertia J2, and the three opposing torques are there in the opposite direction, that is in the anti-clockwise direction. You will end up with this as. Maybe you can try a few examples. So you can just think of writing it for. So just think of this. Assume that there is a friction here, there is a spring constant. Let us say it as K1, let us say this as M1, and let us consider there is a friction, and this is in turn connected to one more mass which is having M2, and there is a friction between M1 and M2. Let us call it as B12, and let us apply the force to this M3. So this is, let us assume that this is connected to a free wheel. So let us assume that there is a B3 which is a friction between M3 and this. Let us name it as simply K1. Sorry, K1 is already written here. Let me write it as K23 because it is between 2 and 3. Let us. So because now this is, let me write it as a spring 1. So this is spring K1. So for clarity. So you can try out what is the transfer function for this. Maybe in the next video I will share the answers. Of course it's a very simple thing you can think of. Fine, we will see in the next